Hi, welcome back. In this video, we're going to talk about evaluating piecewise functions. But let's first talk about what it means to have a piecewise function. What is a piecewise function? As you can see here, this function is broken up into three different parts. Here we have a parabola, here we have a constant, and then we have a line. In Algebra 1 or Algebra 2, right, in previous classes, you spoke about how to graph a quadratic, or a constant, or a line, absolute value functions, all kinds of functions. Well, now in college algebra, we're going to talk about how do we merge a few of these equations into one. Right? As you can see here, we're dealing with a quadratic. But it's not all of the quadratic. It's not going to keep going. It stops at 1. So we can say that it's everything less than or equal to 1. And then after 1, it jumps into a different function. It jumps into a constant. And as you can see, the constant equals 3 for everything between 1 and 2. And then after that, it turns into a y equals mx plus b. This is a linear function. The slope is 1 over 1, and the y-intercept is eventually going to be 0. So this is actually y equals x. But it's for everything greater than 2. Now together, all three equations together create one function. And this is why we call it a piecewise function, because it can be broken up into different pieces, where each piece represents a different kind of graph. So today we're going to talk about how do you look at a piecewise function in terms of a graph or as a function, and how do we evaluate for those pieces. Let's get to it. As you can see here, we have a parabola, we have a constant, we have an absolute value, we have all these different equations. I want to know, what is the value, right? Here we have f of x. What is the value when x equals to 0? So I go to the x-axis, and when x equals 0, the function exists here at 2. Here, what happens when x equals negative 4? I go to the graph when x equals negative 4, and the function exists here at 1. Similarly, when x equals 1, the function does not exist here, there's a hole, but it does exist here at the top at 2. And then we have when x equals 3, the function equals 1. Right? We want to think of f of x as a function of x, where this is my input. So here I'm given all of the inputs. That's why I went to the x-axis to find the output. As you can see below, we are now given f of x, and we want to solve for x. Another word or another variable for f of x is y. This is the same thing as saying y equals 3. When y is equal to 3, or when the output, that's supposed to be a t, when the output is equal to 3, what is the input? So I go to the y-axis, I'm like, when does my function equal 3? And I can see that it equals 3 up here. Right? My graph is equal to 3 here. When x equals 4. When y equals 1, what is the input? So I go to 1. Now notice how this imaginary line at 1 crosses multiple times. We have it here, here, not here, but we do have it here. We have it at 3 locations. Sorry about that. We have it at 3 locations. So when x equals negative 4, negative 2, and 3, the output is 1. And you can see that here. 3, negative 2, negative 4. What about when f of x equals 4? What is the x value? Notice how if I go to 4, there are no values that exist at 4, right? This would give us no solution. There's no values where the outcome is 4. It's not part of our range. So this is an example using graphs. Now let's talk about how would we do this if we were not given graphs, right? We can look at the x-axis for these, we can look at the y-axis, and work our way to the graph to find the locations. Very similarly, now we're going to be working with the actual function. As you can see, the graph is broken into 3 parts. There's 3 equations for these particular domains. So when x equals 0, which part of the graph will that exist in? Well, this means everything less than 2. Here is when x equals 2, and here is between 2 and 6, not including the 2, because it's greater than 2, but it equals the 6, right? So 0 is not between 2 and 6, it's not equal to 2, 0 is less than 2. So 0 is going to exist in this function when f of x equals x squared. So all I do is I take my x and I plug it in for x. I plug the 0 value for x. And since the function was x squared, I do 0 squared, and that gives me 0. What about when the function equals 2? Well, the 2 value exists right here, which means the output will be 6. When x is equal to 1, 1 does not exist between 2 and 6. It doesn't exist here. It exists here when it's less than 2. So I plug 1 into this equation. And that's my output. What about at 4? 4 exists between 2 and 6. So I'm going to use this equation. And I get 10 minus 4. The only difference between our graphs and our equations is that now when we plug it in, we're plugging it into an equation to solve for it. While over here, when we plugged it into the value and we matched it into the quadratic. This was x squared. This was another equation, right? But we're still evaluating. If you are struggling with evaluating, there is another video before this one where I talk about how do you evaluate just one function alone. And all we're doing here is we're breaking the function into 3 different pieces or more and evaluating the function at those locations. All right, guys, I hope this has helped. Please let me know if you have any questions. And as always, we'll calculate later.